Welcome back to the deep dive. Today, we are opening up a bit of a cold case, you could say, in material science, almost half a century old now.
That's right. We're talking about steel. Specifically, a phase transformation that's, well, notoriously tricky to pin down. Bainite.
Bainite. Yeah, for decades, metallurgists have really gone back and forth on how it forms. Is it growing slowly, atom by atom, like diffusion?
Or does it form suddenly through a kind of coordinated shear movement, more like martensite? It's been a long debate.
It really has. And you mentioned it's the least understood transformation. Why exactly?
It just forms in this really awkward temperature window.
Yeah.
It's cooler than where ferrite or perlite form, which are definitely slow diffusional processes.
It's okay.
But it's hotter than where martensite forms, which is this incredibly fast, almost purely mechanical shear transformation. Bainite's stuck in the middle.
So that awkward middle ground, that's where the argument lies then. Is it fundamentally diffusional, like Widmanstätten ferrite growing with these little atomic ledges?
Or is it fundamentally displacive, like a shear transformation that maybe just lets the carbon atoms sort themselves out later?
So to get some answers, we're digging into a specific study from 1979, a real landmark paper.
Absolutely. The researchers were clever. They designed a very specific steel alloy just to tackle this question. It was an iron-carbon-manganese-silicon alloy, specifically Fe 0.43C 3.00 Mn 2.12 Si.
Okay, lots of numbers there, but the key one.
That's silicon. 2.12 weight% silicon. That's quite a lot, and it's really the star of the show here.
All right, let's unpack that. For listeners maybe not deep into metallurgy, why add so much silicon? What's its role?
Silicon, it's well known for strongly inhibiting the formation of cementite, that's iron carbide, Fe3C.
Right, the hard stuff in steel.
Exactly. And in most steels, when bainite forms, carbides tend to precipitate out almost immediately, either between the ferrite plates or inside them.
Which messes up the observations.
Totally. It removes carbon from the picture right away and makes it incredibly hard to figure out the fundamental mechanism of how the ferrite itself is forming. Is the carbon leaving during formation or after?
Ah, I see. So the silicon acts like a spoiler for the carbides.
Precisely. By adding tons of silicon, they effectively slam the brakes on carbide formation, at least at the higher bainite temperatures. It let them isolate the actual ferrite formation mechanism without that immediate chemical interference.
So this special alloy gave them a cleaner look at the underlying physics. Got it. Our mission today, then, is to follow their evidence, the kinetics, the microscope work, and see how this unique setup really tipped the scales heavily towards the shear theory.
That's the plan. Let's follow the clues.
Okay, let's start with the kinetics. The timing of the transformation. We usually talk about upper bainite and lower bainite formed at different temperatures.
Right, that's the classical distinction based on how it looks, the morphology. But the first kinetic clue here was something called the incomplete reaction phenomenon.
Incomplete, meaning it just stops.
Pretty much. The bainite transformation often just peters out, even if you hold the steel at temperature for a really, really long time. The paper mentions like 32 hours at 452 Celsius.
Wow, 32 hours and it's still not done?
Nope, it stops, leaving behind a fair bit of the original phase, austenite, untransformed. We call that retained austenite.
And that tells us?
It tells us the transformation isn't just about reaching the lowest energy state, like simple thermodynamics might suggest. Something physical or kinetic must be actively stopping it.
Interesting. Okay, so what else did the timing reveal? They used dilatometry, right? Measuring expansion.
Yes, to plot the TTT curve, time temperature transformation.
Mm-hmm.
And they didn't just find the expected C shapes for upper and lower bainites starting.
This is where it gets really interesting, I remember.
This is where they threw a real wrench into the works of the dominant theory at the time. That was the solute drag model.
Right, the solute drag model. Remind us that basically said alloying elements get stuck at the moving interface and slow it down, causing a kinetic slowdown, or bay, at certain temperatures.
Exactly. The idea was that elements like manganese or silicon would literally drag on the interface as it tried to move, slowing down the diffusion needed for growth.
Makes intuitive sense.
It does, but that model could really only account for one main kinetic bay, caused by the drag effect of the primary solute. But these researchers in this specific Psi-M steel, they found three.
3 distinct bays, not one.
3 separate dips or slowdowns in the transformation rate on the TTT diagram. One main one, the typical B temperature, but also others separating upper and lower bainite and lower bainite from martensite.
Whoa. Okay, 3 bays. How does that contradict the solute drag idea?
Well, it's just kinetically inconsistent.
Right.
How can one continuous drag effect cause 3 distinct slowdowns? It doesn't add up.
Right.
And there was more. The chemistry itself argued against it. Silicon, the main alloy here besides manganese, actually increases the activity of carbon. It should make carbon want to move more easily, not less.
So if solute drag, particularly involving carbon, was the main control, you wouldn't expect such a strong slowdown, such a pronounced B temperature bay.
Exactly. You'd expect the bay to be weakened, maybe disappear entirely, with that much silicon boosting carbon activity. But it was strong. It pointed towards a mechanism that wasn't primarily controlled by simple diffusion or solute drag.
Okay, so the kinetics alone really casts serious doubt on the purely diffusional models like solute drag. That's pretty compelling.
It was a major blow to that school of thought.
So let's shift from the stopwatch to the microscope then. What did they actually see when they looked at the microstructure? Let's start with upper bainite, the higher temperature stuff.
Okay, so remember, the silicon's doing its job here, suppressing the carbides. So upper bainite in this specific alloy was defined as just an aggregate of the new phase, bainitic ferrite, and the leftover high carbon retained austenite. No carbides to complicate things.
They got their clean lick at the ferrite formation.
They did, and the shape of it, the morphology was telling. It wasn't smooth plates growing steadily. It was this interwoven, almost feathery branching structure.
Like fingers interlacing?
Sort of, yeah. Very complex. And that kind of shape is really hard to explain if it's growing by slow, steady diffusion across ledges on the interface.
It doesn't sound like orderly growth.
Not at all. It looked much more like it formed through lots of little rapid bursts like tiny martensitic jumps, creating small subunits that then link up.
Okay, the shape suggests something rapid and maybe shear-like. What about defects inside the structure? Did they find anything there?
Oh, absolutely. This was crucial. The bainitic ferrite itself had a really high density of dislocations.
Which implies?
High internal stress. Something mechanically intense happened to form it, but the really telling part was in the retained austenite, the stuff left behind.
What did they see there?
They saw planar faults, like stacking errors, and actual visible slip steps right at the boundary between the austenite and the new ferrite.
Slip steps, like the austenite crystal lattice literally slipped or sheared.
Exactly. And even more, they did X-ray analysis and found a strong correlation. The amount of retained austenite was directly linked to the crystallographic texture specifically, the orientation of the planes in the austenite.
Okay, planes. Why is that particular plane orientation so significant?
Because the planes are the easiest slip planes in austenite's crystal structure. Finding slip evidence there and seeing that the amount of transformation depends on the orientation of those specific planes.
It means the austenite is actively deforming, slipping on those planes to accommodate the new bainite phase as it forms.
Precisely. The parent material isn't just passively sitting there while atoms diffuse. It's physically straining, shearing to make room. That physical accommodation is a dead giveaway for a displacive, shear-based transformation mechanism.
That makes a lot of sense. The formation itself involves mechanical deformation.
Okay, so that's upper bainite. What happened when they tempered it? Did carbides eventually form?
Yes. They heated the UB structure with its ferrite and high carbon austenite to around 500 degrees C.
And the retained austenite finally decomposed. Carbides nucleated, interestingly, right at the interface between the austenite and the ferrite, and then grew into the austenite.
Consuming the high carbon austenite.
Right, and initially it wasn't even cementite. It was a temporary transition carbide, a specific iron-silicon manganese carbide, reflecting the alloy elements trapped in the
A
austenite.
metastable phase first.
Yes, which was then later replaced by the more stable cementite. This whole sequence, ferrite forms first displacively, carbon gets pushed into austenite, then carbides precipitate later upon tempering reinforces that carbide formation is secondary, not primary, to the main event.
Okay, upper bainite strongly points to shear. What about lower bainite, formed at lower temperatures? Does it tell the same story?
It provides equally strong evidence, maybe even more directly, but focusing more on the carbon. Structurally, lower bainite, it has much less retained austenite compared to UB. Its signature feature is those fine, plate-like or lath-like carbides inside the bainitic ferrite itself, intralath carbides.
And were these carbides cementite in this alloy, even with the silicon?
Yes. Surprisingly, they identified cementite even at very short transformation times, like just 2 minutes at 300 degrees C. The silicon didn't fully suppress it at these lower temperatures.
Interesting. Did they check for other types of carbides, like epsilon carbide?
They looked, but didn't find epsilon carbide. They suggested the high manganese content might have stabilized the cementite phase instead.
Okay, so cementite forms early in LB. Now, there was another theory floating around for LB, right? Something about a eutectoid reaction.
Yes, the idea that lower bainite might be the product of a metastable eutectoid reaction, like austenite transforming directly into ferrite plus epsilon carbide, or maybe ferrite plus cementite.
A direct two-phase reaction at the interface. How did they test that?
Pretty definitively, they took samples that had partially transformed to lower bainite, containing ferrite and cementite, and then quickly heated them back up and upquenched to a temperature above where this supposed eutectoid reaction should occur.
And if it was a eutectoid, the cementite should have dissolved back into the austenite phase.
Exactly. But it didn't. The cementite remained undissolved. So that ruled out the simple metastable eutectoid theory as the primary formation mechanism for LB.
Okay, another theory bites the dust. So if the carbides aren't forming at the interface via a eutectoid and they're appearing inside the ferrite laths,
Then they must be precipitating out from the ferrite itself after it forms. And for that to happen, the ferrite must have formed with way more carbon dissolved in it than it should be able to hold at equilibrium.
carbon supersaturation.
Carbon supersaturation, that's the key fingerprint of a displacive transformation for bainite. The ferrite lattice forms so fast by shear that the carbon atoms don't have time to get out of the way and get trapped inside, exceeding the normal solubility limit.
And they found direct evidence for this supersaturation.
Two really strong pieces of evidence. First, they occasionally observed mechanical twinning within the lower bainite ferrite laths.
Twinning, that sounds pretty dramatic mechanically, like in martensite.
Very similar to martensite twinning in this alloy, yes. It happens on specific crystallographic planes, the planes in ferrite. Twinning requires a very high internal stress or yield strength in the crystal.
And the trapped supersaturated carbon provides that stress.
Precisely. Dissolved carbon drastically increases the strength and internal stress of the ferrite lattice. They estimated the supersaturation in the LB ferrite to be around 0.25 to 0.38% carbon, enough to potentially trigger twinning under the transformation stresses. It's strong mechanical proof of trapped carbon.
Wow. Okay, twinning is one piece. What was the second?
The second came from how the carbides precipitated. As we said, they formed inside the laths. Critically, they weren't observed at the very, very earliest time, suggesting precipitation happened after the ferrite formed.
Right.
And when they did appear, they often precipitated on more than one variant of their crystallographic habit plane within the same single ferrite crystal.
Multiple orientations of carbide plates within one ferrite grain. What does that tell us?
It's classic evidence for precipitation from a supersaturated solid solution. If the carbides were forming at the moving interface during growth, you expect them to have a single, unique orientation relationship with the austenite they grew from. But forming later, inside an already formed, supersaturated ferrite crystal, allows them to nucleate on multiple crystallographically equivalent variants of the precipitation habit plane.
Ah, I see. The location and the multivariant nature point away from interface formation and towards precipitation from within.
Unmistakably. It's strong evidence that the ferrite formed first by shear trapping carbon, and then the carbon precipitated out as cementite internally.
Okay, this is building a really solid case. We've got kinetics, UB defect structures showing slip, LB showing supersaturation via twinning and precipitation modes. It all points to shear. But was there like a final visual confirmation? Did they see the shear happening?
As close as you could get in 1979, this is maybe the most direct visual evidence. When they look very closely at the interfaces where the lower bainite plates were actively growing into the austenite, they observed distinct spikes at the advancing tips. These weren't smooth, curved interfaces. They were sharp, pointy features, almost like little javelins pushing forward.
Spikes, not like the feathery UB, but sharp points.
Sharp points. And crucially, these spikes had a relatively constant width.
Constant width. Did they measure it?
They did. They estimated the width of these spikes to be roughly 0.2 microns. And this width seemed consistent, regardless of the exact transformation temperature within the LB range.
0.2 microns. That's tiny, but incredibly specific and constant. What does a constant width spike advancing into the austenite signify?
It's considered really strong metallographic evidence for the idea that bainite grows by the repeated formation of small, discrete displacive shear units.
So not a continuous, smooth growth front.
No. It suggests the interface advances stepwise. 1.2 micron unit shears, transforms, then another one nucleates right next to it or at its tip and shears and so on, like little building blocks snapping into place via shear.
Repeated nucleation and shear of subunits, that's a fundamentally discontinuous growth mechanism.
Exactly. It's the visual confirmation of the shear model operating on a very fine scale.
Wow. So let's just quickly synthesize this. If you pull all the evidence together from this one carefully designed Simon steel.
The picture becomes very clear. The kinetics, with those multiple TTT bays, directly contradicted the main diffusional theory, the solute drag model.
Right.
The upper bainite morphology, the high dislocation density, and especially that accommodation slip seen on the austenite planes, showed that physical shear and strain were integral to the process. Then lower bainite provided proof of carbon supersaturation in the ferrite through mechanical twinning and the way the carbides precipitated internally on multiple variants.
Trapping the carbon.
Trapping the carbon. And finally, the direct observation of those constant width, 0.2 micron spikes at the LB interface, provided visual evidence for growth via discrete shear units.
So the silicon really did its job by sidelining the immediate carbide issue. It allowed all these other mechanical and kinetic clues pointing towards a displacive mechanism to come shining through.
Absolutely. It strongly suggested that bainite at its core is a shear transformation, much like martensite, but one that's immediately followed or accompanied by carbon precisioning or precipitation, depending on the temperature.
A really elegant piece of experimental design and analysis. But the researchers had one last thought, didn't they? Something about the variability they saw.
They did. They pointed out that even in their controlled experiments, they saw significant variations in how much bainite formed, the extent of the reaction, just based on things like the initial crystallographic texture of the austenite grains, purely physical effects.
Not chemical composition, but the physical arrangement of the crystals.
Exactly. And this led them to a final, almost philosophical point that still resonates today.
Which is?
That the fact that these purely physical variables, texture, internal stresses, accommodation strains, can have such a dramatic impact on a phase transformation really highlights a shortcoming in many of our traditional thermodynamic models.
Because those models often focus purely on chemistry and energy.
Right? They often treat the material as a uniform continuum and ignore the complexities of crystal structure, defects, and local stress states. This study was a powerful reminder that you can't fully understand phase transformations, especially complex ones like bainite, without properly accounting for these physical factors.
So even though this 1979 study provided strong evidence for the shear mechanism, the challenge remains to build theories that fully integrate that mechanism with all the physical realities of a real material.
Precisely. How do we mathematically capture the interplay between the thermodynamics driving the change and the physical constraints and effects happening at the microstructural level? That's still a major frontier in material science.
A fantastic deep dive into a classic piece of research. Thanks for unpacking that.
My pleasure. It's a great example of how clever experiments can shed light on really fundamental questions.